So this is almost perfectly timed. You'll see why in a moment. I realized actually that for some reason I've ended up with today's talks are vaguely obsessed with numbers. Trisha and I did 97 things every Java programmer should know, so now we're going to do 6 impossible things. You've seen what is possible. I'm going to add 6 more things. And so my name's KEVLIN HENNEY. I'm an independent consultant, trainer, whatever. And professional dilettante. I like kind of nerding around stuff every now and then. And sometimes I'm not talking about the writing of software. I'm talking about the kind of the edges of possibility, just kind of linking this to weird bits of computer science and physics and so on. So whether or not anything I'm going to tell you is going to be entirely useful or not, I honestly can't tell you. It's for you to figure out. And you can find me in a number of places. Let's just assume that this works. Oh, no, it doesn't. Delightful. So that is a piece of machinery that is no longer working. No, there we go. You are now working. Awesome. So you can find me in a number of places. I've started losing track, but I'm kind of everywhere. But that's not what we're here for. We're here for this. 6 impossible things. This comes out of a quote from the White Queen. Sometimes I believed as many as 6 impossible things before breakfast while I'm offering you the same possibility before lunch. Perfectly timed. And when I say impossible, I don't mean, ooh, that's a bit tricky and that's a bit hard, that's going to be really difficult. I mean impossible. Genuinely as in, to do this violates things like physics. Okay, as we currently understand it. If you tell somebody, oh yeah, that's certain, every now and then people try and add to this list. There are other things I could add to this list, but sometimes I get people making suggestions, and I say, no, that's just hard. Well, humans can't do it at the moment. No, but in 10,000 years they might be able to. That's possible. I mean impossible. So let's be very clear. The terms of reference, impossible means it is not possible. It doesn't mean, oh, that's really tricky and it's going to be really hard for humanity at this point, or Java. It means you can't do it, and there are reasons why. So I'm going to do this as a countdown. So we start off. So everything is named on the assumption. Representations can be infinite. Now, some of these, when you look at it, you go, well, of course representations can't be infinite. Nobody would ever assume that. Yeah, nobody ever says it like this. This isn't the kind of thing that comes out in conversation. First of all, we need to get a better understanding of infinity. A lot of people think of infinity as a number. It's not a number. Okay, so that's the first thing. And sometimes we use it in exaggeration. So, the infinite possibilities. No, they're actually all finite. It's just the number is ridiculously so far beyond human comprehension that there's no way we would even think of that as possible. Infinite means infinite. It means without finiteness. And there's another point here, and there's different takes on physics, but I'm quite hardcore on this one. There are no infinities in the physical universe. Infinity is a mathematical concept, not a physical one. Whenever you hear a physicist going, oh, well, this gets to infinite density, or this takes... That's a very polite way. You need to learn how to listen to physicists. When a physicist says that, what they're actually saying is, oh, our theory's so screwed at this point. Infinities mean it doesn't work. That's a polite way of saying that, yeah? Computer scientists have a different way of dealing with these numbers. Whenever sort of the possibility of infinity crops up, they just say many. 0, 1, many. Yeah, how many? Oh, just stuff, lots, many, turn away from it. Physicists have a habit of looking at it and going like, that's not possible. Mathematicians actually have a very different take on this. So you might say, well, yeah, but KEVLIN, I can go and find infinity in the library. In fact, I can find it in 2 flavors. If I go and look at double, I can get a negative infinity or I can get a positive infinity. So what are you talking about? It's like, no, these are representations of an idea. They are not the thing itself. They are not the count of infinity. They're just like, oh, actually, no, we've got no way of representing this. Here's a placeholder for something that is not a number. We'll come back to not a number in a bit. You might say, well, look, if I divide 1 by 0, does that not give me infinity? Yes. In IEEE 754, that's what happens. That doesn't mean it is infinity. It just means, actually, that's a bit tricky, because if I just remove the points from that, what does this give you? It does not give you infinity. It gives you an arithmetic exception. How can we have these 2 radically differing behaviors? Because formally, in the kind of mathematics that we're dealing with, This is undefined. Mathematics does not define this. It's not a case of like it's a bit big. Division by 0 is genuinely not defined. That's why you can make any behavior you want, technically. So why is this a problem? Well, because obviously we're not going to get something. Real numbers are not real. So before 97 things, there we go, the obsession with numbers. Before 97 things every Java program should know, a number of years ago, I edited this book, 97 things every program should know. And one of the pieces that I got was floating point numbers aren't real. And in it, Chuck said, real numbers have infinite precision and are therefore continuous and non-lossy. Floating point numbers have limited precision, so they are finite. And I love this, they resemble badly behaved integers. That's a great way of looking at it. Yeah, floating point numbers are badly behaved integers. But the question then comes, is how badly behaved are integers to start with? I mean, it turns out they're quite bad. So floating point is like bad on bad. Let's find out how bad they are. So back in 1983, John Bentley wrote this column, Communications to the ACM. He had a column during the 80s, programming pearls. And these were collected into a couple of volumes, which I kind of learned an awful lot from them. And he wrote this piece on writing correct programs, and he presented within it a binary search algorithm. Okay, different to the binary search algorithms that existed up until that point. You can see there's a nice little three-way division here. What we're actually looking for, and what makes this binary search interesting, is not simply that we are going to take a sorted sequence of things and say, right, you're looking for a value, it's in there or it's not. It's and then the variations you normally get of a binary search algorithm, it's in there at this position or it's not. This one's different because it says it's in there at this position, or it's not in there, and if it were there, it would be here. Which is great for insertion. Okay? And he proved that this was correct. And this is kind of, as people were getting into the idea of maybe program verification might be a way forward. As here in 2024, we can say no. Okay? That wasn't where program verification led us. But he said one of the major benefits of program verification is it gives programs a language in which they can express this understanding that they might have of something. And this is actually the fuller form where he kind of annotates with what effectively are assertions. These are truths that must be true at this point, and therefore you can create a proof around this. These techniques are only a small part of writing correct programs. Keeping the code simple is usually the key to correctness. But he's not blinding himself to the fact that simplicity matters. Okay? That's going to become important. It's also foreshadowing. But here's the thing. Ultimately, code is written by people. Human factors intervene. On the other hand, several professional programmers familiar with these techniques have related to me an experience that is too common in my own programming. When they construct a program, the hard parts work the first time, while the bugs are in the easy parts. Yeah, you had that experience? You're so focused. Oh, this is tricky. The eye of Mordor in your mind is focused on this problem. You root it out. Yeah, I've totally nailed that. And then there's an off by one error somewhere else. Or something trivial you forgot to update. Yeah? So maybe that means that the hard parts are actually easy and the easy parts are the hard ones. I'll leave that paradox for you to resolve. And this is also foreshadowing. So let's take you back, or take you forward from 1983 to 2006. This was in the Java library. It's written by Josh Block, who was a student originally of John Bentley's. And it's a binary search. You know, this is great. And it turns out that this binary search algorithm worked absolutely fine up until around the early 2000s. So this was in Java 1.2, late 90s. It was proven correct in the 1980s. It was discovered to be incorrect in 2006. Because it turns out that if you are using int, which is a 32-bit, let's get rid of the negative domain, it's 31-bit, okay? It turns out that you are never going to have that much memory in the 1980s. To have an array with basically 2 billion elements, that's not a thing in the 1980s. However, it is a thing in the 21st century. It turns out that numbers have a particular behavior when you hit very large arrays. And certain assumptions don't work, like this one here. that if you want to take the midpoint, binary search is about binary chopping. And you do this by, oh yeah, we'll take these two numbers, we'll add them, divide by 2. That's how you're taught at school, because that is how you find the average of two numbers, or the midpoint. There's only one problem. Integers are not integers. That's why I think actually the fact that Java uses an abbreviation int is appropriate. Integers are infinite in extent. Ints are not. They are truncated, like the word. Okay? And it turns out that when you take a really large number plus another really large number, it turns into a very negative number, which you then divide by 2, and all hell breaks loose. We've discovered the negative domain, and it's really negative in this case. So yeah, this doesn't work. It's rooted in an assumption. We can actually see the assumption in the original paper. There, he's using maths. This is why mathematicians make such bad programmers. And I've probably pissed off a few of you there, but you know it's true. I've worked with you. So the point here is just like, yeah, this doesn't work. There's a certain irony also that the paper is called Writing Correct Programs. This is universal irony. I mean, that's kind of that is a long mic drop. Okay, it's 20 plus years. So yeah, but we already knew this, and it was actually foreshadowed in 1972 in a piece that Dijkstra wrote, Notes on Structured Programming. I think he wrote it in 70. It was included in the collection in 72. I have assumed perfect arithmetic, and in my experience, the validity of such proofs often gets questioned by people who argue that in practice, one never has perfect arithmetic at one's disposal. Admissible integer values usually have an absolute upper bound. Real numbers are only represented to a finite accuracy, etc. So what is the validity of such proofs? If one proves the correctness of a program assuming an idealized perfect world, one should not be amazed if something goes wrong when this ideal program gets executed by an imperfect implementation. So yeah, we need to fix that. So another way of finding the midpoint, which is mathematically equivalent but not computationally equivalent, is this. Josh Block actually suggested in the blog post that he wrote about it that you should use an unsigned right shift. And he said, probably faster and arguably is clear. I'm prepared to take that argument. I am prepared to have that argument for a number of reasons. Alberto Savoia, writing about this in Beautiful Code in the 2000s, 2007 if I recall, said, probably faster, but maybe obscure to most Java developers, including me. That's more like it. But ironically enough, in one of John Bentley's collections, More Programming Pearls, there is this quote from Guy Steele. This is the late 80s this was published. If the programmer can simulate a construct faster than the compiler can implement the construct itself, the compiler writer has blown it badly. This whole right shift nonsense to divide by 2, I still see people doing that. It ceased to be a relevant practice in the late 1980s, early 1990s. Okay? If anybody ever justifies that, ever uses that as a justification, give them some space. For like a lot of space. Yeah? Not like an isolation zone, a moat, the whole thing. The point there is, no, it's not going to be that much more efficient. It's not going to be efficient because that's what the compiler, it's a division by 2. You know what? I'm a computer. I know about this stuff. It turns out compiler writers know about this stuff. It turns out the VM's optimized for this stuff. That's not your problem. But there we go. These techniques are only a small part of writing correct programs. Yeah? Keeping stuff simple. So let's look at another challenge. Every question has an answer. And what I mean by that is that on the terms of a question, you can offer an answer within that framework, or that type, or that concept. Let's have a look at a certain example. This one is one I use quite a lot. It comes from quite a while back, probably about 10 years back. Facebook. Your feedback will be used to improve Facebook. No, it wasn't. Thanks for taking the time to make a report. How much time? That's quite a lot of time. In fact, it's quite a lot of negative time. Yeah, negatives seem to be playing a strong role today. How do we explain this? 31st of December, 1969. I mean, that predates actually quite a lot. It's before the beginning of... hang on, that's suspiciously close. You need to remember that the universe is implemented in C. Okay? And the universe is implemented in C. In other words, you keep going, there's C, there's the C layer. It's down there somewhere. And that means that a lot of the quirks that we have shining through in other languages and libraries can be traced back to C and conventions embodied in C and classically Unix. And there, ultimately, you get time from a function called, imaginatively enough, time. The value of time in seconds since the epoch is the IEEE standard, the POSIX standard. When's the epoch? Well, it turns out that you don't have to go very far because there's enough failures to tell you when the epoch is, even if you didn't know it. I was sent this one a couple of weeks ago by Paul Riker. There we go, there's the epoch. Yeah, you can find it available all over the internet. Somewhere there is a zero value, and boom, suddenly you've got midnight. The cusp of midnight as we join the 1970s, as we enter the 1970s. There it is, 1st of January, 1970, the beginning of time. What I like about this is that it basically means I was born before the beginning of time. And when 32-bit time runs out, I'm hoping to still be alive, because it's 2030s, that will mean I will have lived past the end of time, which will make me immortal, technically. I won't be accepting arguments at this time. Now, when I first encountered this, my initial suspicion was that it was time zones. Because I thought initially, wait a minute, Facebook, if there's something been zero initialized, and I'm in the UK, Facebook's based west of that, so that would shift it, if we adapt time, that would shift it back onto New Year's Eve, 1969. It's like, okay, that makes sense. But as I started looking at this, I started realizing, actually, there's something else going on here, because the universe is made of C. I have various copies of the C standard at home, because why wouldn't you? Let's go and have a look at time in more detail. The value -1 is returned if the calendar time is not available. Oh, that's really cool, because you see -2 is 2 seconds back into 90, is 2 seconds back from the epoch. -1 is either 1 second or, yeah, brilliant. Use an error value as a normal value. Nice one. So actually, this is far more plausible that what's happened is time was not available. We nudged 1 second back. And instead of checking it as an error code, it's just like, yep, this is actually a legit time, rather than saying we don't have time available. Because people think that time is a thing that is always available. I have bad news for you. I'm going to follow the wisdom that we find in Interstellar. And the character, Dr. Amelia Brand, she says, we need to think of time as a resource. And when you recognize that something is a resource, you recognize that it might fail. It's not always available. When you access time, it's not just freely available in the air. It's not some magic global. It is an operating system resource, and therefore you may fail to access it. Now, at this point, we're going like, oh yeah, but we could fix that by choosing certain representational choices. Yeah, there are certain representational choices that have proven to be very popular in the floating point space. Thank you, Lufthansa, for the deep insight that NaN, I tried to parse NaN, but it's not a number. That is deep, self-referential, and true. A lot of people think that NaN was given to the world by JavaScript, because that's what they normally see. They experience this. It's like, no, this is 1980s, IEEE 754. The point here is this says, honestly, we don't have an answer to this. And that's the most important thing. We don't have an answer to this in the frame in which you asked it. If I asked you, what is the square root of -1 as a double, I can't answer you that question. That's not a possible question. I cannot give you a double that has that holds a number. That's not possible. We are answering outside that context. Why does this have practical implications? You ever had that experience? You go onto a page or an app, and it tells you, hey, there's 0 things here. Your heart skips a beat, because you put lots of money into whatever it is you just bought. Tickets for a gig, your bank account, whatever. And there's a moment, there's a flash of, it's 0. Holy shit. And then a moment later, just kidding. You got 3 things there. Your money's fine, your tickets are fine. It's all good. There's a technical term for this. It's called bad design. If you need other words for it, let's explore this. So what's actually going on here is that somebody has mismodeled this. To quote John Carmack, a large fraction of the flaws in software development are due to programmers not fully understanding all the possible states their code may execute in. People don't fully have a grasp of the state model of what they're building. they end up, basically, here's the state model that somebody implemented. Whatever you've got, it's displayable immediately. And currently, we have no initialized value. It's an empty collection of orders, so therefore the size is 0. This is a leaky abstraction. I've made the mistake that I've said that initially this is displayable. No. And then, boom, it updates. And your heart kind of does that thing. Oh, we're going to get radical here. There's 2 states. There's one called loading. You know what we display during loading? Not a number. And then it's displayable, at which point we say, hey, your stuff's here. We don't say, hey, you've got no stuff. Oh, by the way, I was just kidding. That's how you do it. This is the practical point. The idea is that, yes, you may have a collection for orders, but you're not displaying the collection. You have a different model there. You don't know the answer. It is not yet determined. I cannot give you a number because that number is not yet available. I cannot answer it as an int, or even -1. Now, this has other implications. It's a great book, Logicomics, about kind of the search for truth. A lot of stuff on Bertrand Russell, Kurt Gödel, Frege, a bunch of other mathematicians and logicians, kind of telling you the state of mathematics in the 19th century and early 20th century. A bit of philosophy, and it's a graphic novel. There's a lot to like here. I have a nice definition of algorithm. And given that we just looked at an algorithm in binary search, this feels appropriate. Given that algorithms are the stuff of computer science, what is one? A methodical step-by-step procedure described in terms of totally unambiguous instructions. That's what's really important. Which starts at a specified initial condition and eventually terminates with a desired outcome. So, you know, people like sorting. So I'm going to switch to Groovy. I need to know if something's sorted. So I thought, you know, why not just shove it onto one line? So that is how to determine if you've got an array that's sorted. And then I guess I ought to show a sorting algorithm. Here's one of my favorite sorting algorithms, permutation sort. This is what we call an NSFW algorithm. It is definitely not safe for work. We are going to explore all the permutations until we hit the sorted one. Okay? Takes us to, it's got factorial complexity. This is why I say it's not safe for work. Okay? If I want to sort 10 items, that's potentially 3 million actions. That's terrible, and it only gets worse. Why would we ever use this? Well, I use it as a kind of a thinking tool. When somebody says, I say, okay, what are the performance requirements? Oh, we don't have any performance requirements. Honestly, put this in. That person will discover they have performance requirements. Somewhere between we don't have performance requirements and permutation sort is their requirement space. Yeah? That's how you kind of demonstrate, that's how you bring it out. So, yeah, OMG performance. In essence, it's an unoptimized search through the permutations of the input values until it finds the one arrangement that is sorted. Surely there can be nothing worse than this. Yeah, please hold my beer. The essence of BOGO sort is to shuffle values randomly until they are sorted. So a lot of people implement BOGO sort like this. While not is sorted, values shuffle. This is actually not the correct way to do it, because if it's initially sorted, then this goes straight through. We don't want that kind of performance benefit. Whatever you gave me, whatever. Now, you know, the polymath John von Neumann made this observation many years ago. Anyone who considers arithmetical methods of producing random numbers is, of course, in a state of sin. He says like that like a state of sin is a bad thing. That's a different debate. But OK, we'll take that. So we're going to use secure random. There we go. Fine. So the question here is that actually an algorithm? A procedure which always terminates is called an algorithm. It's not guaranteed to terminate. You have no guarantee that with truly random numbers, if you do a random sort, that will ever terminate. Right, but I need to show you this. So back to Dijkstra. Program testing can be used to show the presence of bugs, but never to show their absence. A classic quote. So let's test this. To infinity and beyond, right. We've got the values, we've got expected, we're going to bogus sort the values, and we're going to assert that those are equal. No, not actually guaranteed. By the way, every time I've ever run this, I did not have to wait to the heat death of the universe and beyond. Obviously, it's fairly small, and we're going to get there. But in principle, just imagine that's a more pi, and who doesn't want more pi? So to infinity. So really, what I need to do, I need to have a timeout. I need to basically say that we are expecting that this will terminate sometime around infinity. We'll time out if we reach infinity, and there's a real problem with that. So what we do is we optimize this to 1,000 milliseconds. And that is actually how we deal with certain problems. This is actually how we work around certain problems of non-determinism. What we do is that's not deterministic. Okay, well, what I'll do is I will trade determinism for a clear time boundary. And what I will do is I will say, at the end of a particular period of time, we will either have an answer yes, an answer no, or who knows. We will introduce an answer that is not within our original frame. This allows us to solve things like the halting problem by introducing certain constraints. We're not really solving it, we're working around it. And that's kind of important because this is about truth. Every truth can be established where it applies. What do we mean by that? Well, I'm kind of hinting at a couple of things. I mentioned Kurt Gödel, English translation on formally undecidable propositions of Principia Mathematica and related systems. You've got to love these titles. They're great. They just roll off the tongue. They're snappy. They're direct. You know exactly. Okay, maybe not. Adrian Collier had this nice summary a few years back that basically captures what was going on and is actually played out very much in more detail in that book, Logicomics. There was this idea in the 19th century that towards the end of the 19th century that we were on the cusp of solving everything in science and maths and the world and everything. It was all solvable, and that we would have definite answers and there would be truth, and that mathematics would be proven to be consistent and complete and all the rest of it. And physics, the whole of physics was almost like done. And then a bunch of things happened in the 1900s, including things like quantum mechanics, which really messed things up. And but we had something here. This looked good. 1911, one of the least read mathematical documents ever, Principia Mathematica. 1911, Bertrand Russell and Alfred North Whitehead published Principia Mathematica with the goal of providing a solid foundation for all of mathematics. 20 years later, Gödel's incompleteness theorems shattered the dream, showing for any consistent axiomatic system, there will always be theorems that cannot be proven within the system. Now, you might say, well, that sounds all very nice. What's that got to do with me writing software? Okay, what we're doing is we're saying that you cannot demonstrate certain truths within certain systems. You have to step outside the system and say, oh, actually. This was highlighted in this classic book, Gödel, Escher, Bach, where he explores this in much more detail and more entertainingly. All consistent axiomatic formulations of number theory, which includes programming languages and modern computers, include undecidable propositions. So let's pick on an undecidable proposition. How long is a piece of string? And for this, I'm going to switch to C, because I can conveniently find problems very quickly. If I were to do that, I can do Java, but it would take more code. Strlen, which you need to remember that there was a huge vowel shortage in the 1970s. So here is the string length function. I mean, they can be swung for an E, which I think is a win. And that's going to return some kind of size-related integer. We're going to take a string, which, I mean, we've used up so many letters in Strlen, we're just going to call it S. And what we're going to do is we're going to say, hey, look, there's a bunch of characters, there's a sequence of characters, I'm pointing to them, and we are going to calculate how long that is, because it's going to be null terminated. What we're going to do is we're going to initialize a counter to 0. I'm sure we're all good with that. And then we're going to repeat, whilst that position is not equal to the null character, increment the position, and by the time we reach the end, then we return n. This is great. But there should be some preconditions on this. Well, an obvious precondition is that that pointer should not be null, because otherwise you're not going to go anywhere. Actually, there's another precondition. It's a little harder to state, and I put it in gray, and I've used some funny letters to let you know it's not C. And this is not actually expressible. In fact, it expresses something that we can't actually do, even if we added the operators. It expresses something impossible. It says that there is an n such that the position in the string, Sn, will be null, and for all the positions from the beginning to that point, that address is defined in memory. So there's a bit of a paradox here. I'm basically saying there is something out there and it's defined and every point between it is defined. You will find a null. And if none of this works, then, well, what actually happens? Well, let's actually put this into practice. So here's the kind of, basically, what I'd consider to be a motto of this conference: be excellent to each other. So this is well defined. Okay, I'm going to print it, and we get be excellent to each other, because that's a string that's the right length, and it has a null terminator, and we find the null. That's all good. What happens when I do something a little bit dubious? Like I say, actually, I'm going to constrain this to 5 characters in a way that ensures I cannot have a null at the end. In fact, I can even write it deceptively as if it were something that had a null. So I can write this. And what happens here? Well, you might be lucky. You might be unlucky and find yourself out there in the void. The point here is it's undefined. Maybe it works, maybe it doesn't. It's one of those great bugs. You love those, don't you? Yeah? Okay, let's really double down on this. What if I don't initialize that pointer? Because you see, I'm able to demonstrate the truth of this. Let's actually go back. I'm able to demonstrate, and this is the important thing, we already know this is broken. Why? Because I'm looking at a context outside strlen. In the context of strlen, inside standard C, I cannot prove that it will terminate and have defined behavior. When I step outside the context, in other words, a function that calls it, I can go, well, that's not properly constructed. I can tell by construction that does not have well-formedness. You have to step outside whatever system you're understanding. In this case, it's a very small system. It's one function in standard C. I can't tell the truth of its outcome unless I look at how it's called. I need to know the context. I cannot look at it on its own terms and state its conditions in anything but English. Which means that when I say, this is undefined, that pointer points who knows where, and you will be touching the void. And the point about this, going back to 97 Things Every Java Program should know, there's a lovely contribution from Thomas Ronson, how to crash your JVM. And there are 12 pieces of advice. If you want to crash your JVM, go there. And one of them, write some native code. All of the syntax of C, all the safety of C. Awesome. Now, Adrian actually goes a little bit further with this one. This actually has implications for how we understand machine learning. One premise of many models of fairness in machine learning is you can prove fairness of a machine learning model from within the system, from the properties of the model itself and perhaps the data it is trained on. To show that a machine learning model is fair, you need information from outside the system. You have to step outside it. You cannot tell from the inside, so to speak, and with the data that you've already used. That's actually an implication of Gödel, not just string lengths. We see examples of this if we go back to the pandemic. Sorry to take you back there, 2020, summer of 2020, a Berlin-based artist, Simon Weckert, did a rather interesting thing. He walked around the streets of Berlin with a cart filled with 99 Android phones, second-hand smartphones transported in a handcraft to generate virtual traffic jams in Google Maps. Because Google Maps is sitting there going like, well, that's pretty slow down that road. There are clearly 99 people moving very slowly. There's one person. There are 99 people distributed across vehicles because that's what roads do, not when they're empty, because it's lockdown. The point there is, yeah, it's correlated, but it's not the truth. The point here is we need to be very cautious with this, because we often talk about engagement. Now, what is engagement, apart from getting, what you might do before getting married? Engagement, the state of being engaged, is engagement, is emotional involvement or commitment. I love it when you see people sort of say, oh yeah, our site now has more engagement. Have you gone out and measured the emotional content of people doing that? I think most people are second screening, if you're lucky. Or they accidentally just left it on your page because it was loading so slowly, they actually went off and did something else more meaningful and useful with their time. You have no idea. It's engagement. You are not measuring engagement. You are measuring clicks and shares. You are measuring timeouts. You have no idea if there is a person at the other end. We must be careful not to confuse data with the abstractions we use to analyze them. That's the point. You cannot establish the truth of engagement. You cannot establish the truth of the traffic. Again, be very careful. Now, another one. The future is knowable before it happens. So, the late, great Grace Hopper To me, programming is more than an important practical art. It is also a gigantic undertaking in the foundations of knowledge. That's how to feel good in the morning. You're a developer. Oh, you're not just a developer of software. You are an applied philosopher. Yeah? You wake up every day and you grapple with the thorny problems of reality and constructing a reality of your own making. And the rules that bind it. You are world building. You are exploring thought made real. That's what you want on your business card if you still do business cards. So how do we need to classify the things that we know and don't know. So I'm going to borrow and reframe from Philip Armour's 5 Orders of Ignorance. The known knowns, the thing you know. This is level 0. Level 1, the things you know that you don't know. Then there are the things you don't know. And then there are the things you have no way of demonstrating you don't know until they are known. In other words, you can't predict them. You have no way of running an experiment that demonstrates and flushes out these things. This is what we're interested in, the unknowable unknown. Now, it's the halting problem. Can I create a program that will determine with guarantee whether another program will terminate or not, or another algorithm will terminate or not? Turns out, no, you can't. And we don't know that until we've waited until infinity, but we've recognized that's a problem. So it actually turns out we have an issue here. But let's be very practical about this. This applies, the fact that we do not know the future applies on a daily basis. That's a nice one from Seth Rosen. When naming things like tables, always future-proof. If you sell wine, calling a table wines will be confusing when expanding to beer. Beverages will be confusing when you sell ice. Products will be confusing when you expand to services. So, recommend tables be called stuff or table one. There you go. You've now learned how to future-proof your code. Yeah? I actually worked with somebody, it's so funny, we're doing a code review, and it's just like, yeah, this is all going well. And then I looked at the file name at the top on the title bar, and it said stuff. And I said, Paul, you can't call this file stuff. And he said, well, it's not wrong, is it? And I said, yeah, but it's not exactly the right kind of right, is it? So here's a point. People often talk about, they use these various metaphors, roadmaps. Oh, we have a product roadmap, we have an architecture roadmap, we have a development roadmap. This all sounds absolutely fantastic. We have a roadmap. And you can even go online. And I did this, actually, because, honestly, there was not a lot else to do back in 2020. So I did this, and I sort of thought, yeah, I've been mocking the use of the term roadmap for years. And I thought, I'll go online and see if there are PowerPoint templates for this. Oh, my goodness, are there PowerPoint templates for this? They all kind of look a bit like this. They've got a road on them, and they go, here's the gaps that you fill out, and so you can look really cool with your presentation. There's only one problem with this. It's got one road. If you've got one road, you don't need a map. Okay, I just want you to pause for a moment. This is what a roadmap looks like. It's filled with possibility and complexity. That's why we have roadmaps, because it shows us alternatives. It shows us the tangle of stuff that we're going to use and have to confront and work with. That's the, if you've got a roadmap, in fact, I think the metaphor is great. I just wish people would use it correctly. If you've got a roadmap, show me the roads. If you're showing me one road, we don't need a map. It's just an itinerary. Yeah? This is why we need maps. You're there. In all the complexity of Islington, here you are at this moment. So we can see some great examples of this roadmap. Here's another one. You can tell this one dates back to around 2018. They've even carefully helped you. You know, here's ideas that you can put in there. What I like about this is that it's got 2020 in it. How many people had on their product roadmap major disruption to all development and our customers globally because of a pandemic that redirects the course of human history? No, I didn't think so. Nobody else did either. That is an unknowable unknown. There was nothing you could do before that to know that that was going to happen. Oh, there's a bunch of probabilities. People were reckoning, and the probabilities were stacking up. A lot of people said, yeah, 2020, there's probably going to be some kind of pandemic based on SARS and MERS and a couple of other incidents worldwide. But that's not the same as saying 2020, March is when it hits critical. That was in nobody's plan, because there was nothing we could do before that. Why is this important? Because people often talk about business value, which is itself a nebulous term. I'm not saying you can't make it concrete. Business value to whom? Always ask that question. Business value over what time frame? Business value over 3 months is not the same as business value over 3 years. Is it business value to my customers, or is it business value to our company? I once made a decision a number of years ago that saved us 2 weeks of development work And therefore, we charged I replaced a 2-week solution with a 1-day solution. The customer was delighted. That was business value for them. My boss was infuriated. The point is, define it. If you're going to use it, if somebody using the term business value and they haven't told you what they mean, raise your hand. They're just waffling. But that's not the problem here. The problem is that a lot of development methodologies are telling us to prioritize by business value. You can find this. Open up a book on Scrum. Prioritize your backlog according to business value. That's fantastic. There's only one problem. It's impossible. I don't mean it's hard. I'm not telling you not to do it. I don't have to tell you not to do it because it's impossible. Because you don't know the future. You have no idea what the business value is. Yeah? Everybody has a favorite film of theirs that is maybe a shame-based film, but it's a film that you like but actually bombed in the cinema. Do you think that the studios said, you know what, we're going to spend tens of millions, if not hundreds of millions, on a film, and it's going to totally tank? Well, that's a great idea. What a fantastic business proposition. No, they didn't know the future. It turns out you have no idea what the business value is. If anybody talks in terms of business value and they do not use the word estimate, they are bullshitting. Okay? And if you say, oh yeah, but KEVLIN, you know what we mean, yeah, when we say business value, if I have to come out here and explain actual versus estimate to you, it's not going to be pretty. The point here is that it's an estimate. We don't know the future. Prediction is surprisingly difficult, especially where it concerns it. What I love about this quote is we don't actually know who said it. I mean, I like to think it's Niels Bohr, because Niels Bohr, Danish, quantum physicist, and I think that's kind of cute. If it's a quantum physicist that says this, that's really cool. But we don't actually know. If you go on the internet, you'll probably find that Abraham Lincoln said it. There's loads of people who have been attributed. But what I love about this was said in the past, and we don't know who said it. What hope have we got for the future in this sense? On knowability, distributed systems. There is an idea, and often we are shielded from this by sitting in the IDE, by frameworks, and just, I'll just make a call. And we're aware that calling across the network is a little bit slower than calling something that is local to our process and in the same thread. But it actually engages parts of physics that are going to be quite important. So, just to get a feel for this, Martin Fowler outed me a couple of years back. You ought to know United may have discovered a kink in the time-space continuum over the Atlantic. And what's the kink? Oh, time to destination, 0. Distance, 2,500 kilometers. That's impressive. Let's get a real grip on, the distance between Heathrow and Newark Airport is just over 5,500 kilometers. Not 19 centimeters, 19 light milliseconds. So already we need to confront this point. If you have software running in London, let's say you're in fintech, you've got something in New York, you've got something in London, and somebody says, these two need to be in sync with respect to 10 milliseconds. You cannot do that. It's not hard, it's impossible. Or you've got a Nobel Prize waiting for you, okay? I cannot break the speed of light. Oh yeah, but I'm your project manager and I'm saying you can. No, really you can't. It's not a thing. Now, this actually also has other broader implications. We need to really understand the nature of distributed systems. So I co-authored this book a number of years ago, Pattern Language for Distributed Computing, and in it we gave a definition of a distributed system. It's a computing system in which a number of components cooperate by communicating over a network. True, but dry. Leslie Lamport's definition gives you much better feel for it. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. Yeah, that feels familiar. So this is one about my publisher, O'Reilly, a couple of years back. Fire in California, can't read your ebook in Pennsylvania. We have a problem with location. And the point there is we have the idea of reliability or partition tolerance when a network kind of becomes breaks into two. A router fails, something goes down. You have no way of dealing with that fully. In fact, there's a thing called Brewer's theorem, and it is actually a theorem. It was originally a conjecture, but it was then proven, better known as the CAP theorem. CAP, consistency, availability, partition tolerance. Okay, the idea is you can have any two. You cannot have all three. What we mean by consistency is that everybody who asks anything will get the same answer. Okay, imagine we're dealing with a social media, some kind of social network, and you're there on the phone, you're connected to the internet, your colleague's there on the phone, and you both refresh at the same time looking at the same person's feed. You will see the same thing. You will not get different answers. Okay? Availability, that whenever you look for an answer, you will always see it. Okay? And consistency is basic, there's that. And then there's partition tolerance. In other words, we are resilient against failure. Now, you can have this. You can be consistent and partition tolerant. In other words, in the presence of failure, I can give you an answer, or I can say, I cannot give you an answer, therefore I will give you a failure. Because I cannot show you the right answer, I will tell you the answer was not available. Or we go for this one. Oh, I can always give you an answer, but it might not be consistent with other people's. Caching. And actually, there's an interest. So this is how we deal with partition tolerance. There's actually an edge case here, consistent and available, but totally brittle in the face of any network failure. You can have any two, but not all three. This is effectively a realization of Douglas Adams' Hitchhiker's Guide to the Galaxy. Observation. Philosophers demand rigidly defined areas of doubt and uncertainty. Yeah, that's what we've got. CAP's theorem is Heisenberg's uncertainty principle for networks. You cannot have all three. Does this have practical implications? Yeah, it's to do with state coherence. And we end up with stuff like this every now and then. See the problem? You have two orders, three. I get this so often in things. I'm told, there's nothing in your inbox. I can see there's three things there. These two numbers are different. You are showing me three things, and then you've got another integer that says 0. This might be a fault of micro front ends, and some people blame it on eventual consistency. I blame it on bollocks, because actually the correct answer is you're in the same process. You can see you've got a list. Show me the size of the list. If your integer differs from that, then it's whatever you're showing is the right thing. Or truncate the list to 2 items. The observation here is a feature of a distributed system that it may not be in a consistent state, but it is a bug for a client to contradict itself. That is a coding fault. Nothing more and nothing less. So the final thing, and actually Owen was talking about technical debt in the session before. Technical debt is quantifiable as financial debt. This is a really common one. I see this. I see people using various tools, and I'm not going to name them, that will say, oh, we're going to analyze your code and tell you, you have £453,027.16 of technical debt in your code base. This is pseudoscience. It's not even close. It's just pseudoscience, and it can never be better than that if you are doing this. We need to understand a little bit about the nature of our systems. An observation from Manny Lehman back in 1980. As an evolving program has continually changed, its complexity, reflecting deteriorating structure, increases unless work is done to maintain or reduce it. And this is really interesting because he's basically saying, whenever you do anything, you have to do extra work. It's not because you've necessarily done something bad. You could be doing all the best coding practices. He's basically saying the very act of changing a system that works requires you to do additional work, which we will call maintenance here. It's funny, we've ended up with a different meaning of the word maintenance. That's actually not quite accurate. Maintenance is to maintain the level. If I decide I'm going to go and cook a meal, it is not my, well, let me put it the other way. Put it another way. I don't say, right, I'm going to the kitchen to make a mess, except in jest. But there will be a mess. I cannot make a meal without making a mess. It's a natural consequence. When you are focused on making a change, you need to understand the nature of focus. Focus is the direction of your attention. What you are doing is you are depriving everything else of your attention. By definition, you cannot focus on everything. That's not what the word means. If you are focused on everything, you are focused on nothing. The whole point is, focus is, it's that. My attention is here. That means I have inattention everywhere else. I'm going to miss stuff, no matter how good or well-intentioned I am. So the idea is the very act of doing something with focus is going to cause something to be overlooked. It might be a simple thing. Oh, I could have deleted something, simplified something. It might be more complex. The idea is I have to do extra work. Now, a lot of people come to call this stuff, this mess that accumulates, they've come to call it technical debt. And this is actually a misdirection. It's not that it isn't debt. Debt is not a bad metaphor, but it is a metaphor. The real problem that most people are confronted when they say is, when we say we have lots of technical debt, what they actually mean is that what they're forgetting to ask is, where did the debt come from? It's neglect. The real issue that most companies, teams, and code bases have is a problem of neglect. It's not, the debt comes from somewhere. The debt is an effect. Whenever you see an effect, look for the cause. And the problem, what's the challenge with neglect? Neglect is a thing that you can't see. Neglect is not a thing that happens. Neglect is a thing that does not happen. That's why it's so difficult to identify. There's a failure to do the maintenance. That's the key thing there. That's the bit that we're missing. So it is indeed it is indeed a wonderful metaphor. And actually, I've got this boat here. There's a kind of a thought here. I'm going to give you the software developer's view of this. I've got a boat. We're out on the water. It's got holes in it. It's taking in water. How does a software developer deal with this? Well, some software developers will let the whole thing sink. Other software developers go like, yeah, we're taking on water. That means we've got a lot of water in the boat. You know what? We need to fix our technical debt. We need to get the water out. What does the rest of the population do? They say, oh, that's funny, we've got water coming in. Well, not only do we need to get the water out, but we also need to stop it coming in. I've actually been in a situation with companies where help them with their legacy code, their unmanaged technical debt. And their real problem is that they forgot to stop creating it. They're busy fixing it, the water's there, getting the water out, but they're not solving the problem of how they create it. And it's normally created not through malice, but through neglect. So let's understand where this comes from. Martin Fowler's original blog on it correctly refers to Ward Cunningham as the originator of the debt metaphor, 1992. Technical debt is a wonderful metaphor developed by Ward to help us think about this problem. Like a financial debt, the technical debt incurs interest payments, the extra work you have to do, the extra effort we have to do in future development because of the quick and dirty design choice. But I want to go back to this. First thing is it's a metaphor. The debt, it's a metaphor. It's not a financial debt. It's not the identity. It is the metaphor. It's a way of understanding. It's a framework for understanding it. Think about it. I found myself again cautioning against the category error of treating technical debt, the technical debt metaphor literally and numerically, converting code quality into a currency value on a dashboard. There are a number of challenges with this, but let's just deal with a couple. One of them is sometimes people say, oh, well, you know, we've done it. What we've done is we've gone through and we've estimated how much work it takes to do this, and therefore we've estimated in hours, and then we've multiplied hours by how much a developer costs per hour, and therefore we have an estimate here. This is also a misunderstanding, because technical debt is not equal to the cost of repaying the debt. It is equal to the cost of owning the debt. That's the point of the debt metaphor. It's a complex financial instrument. And to know your debt, it means you have to know the future to understand it fully. And I think we've already addressed that one. This is the point. The message of the technical debt metaphor, not simply a measure of the specific work needed to repay the debt. It is the additional time and effort added to all past, present, and future work that comes from having the debt in the first place. If I have a tool that measures, oh, duplication is bad, and it measures duplication, and it puts a value to it as well, we don't know that that's actually a problem, because if that's dead code, then yeah, sure, we should delete it, but it's not actually causing us any problem. You cannot evaluate this without context. We do not know the answer. We don't have enough context, and most of the context is the future. It's not simply the code base. It's not based on language features. It's a staggeringly naive way to look at it. So yeah, it turns out you can't actually convert it to a financial debt. So with that, I will give you an extra bonus impossible thing. Finishing on time. I acknowledge my weaknesses on this one, but I hope that you have come to appreciate, if nothing else, reality cannot be ignored except at a price. And in this particular case, that price is 5 minutes. Thank you very much for your time.